Welcome to the first video of Chapter 13. Chapter 13 is going to cover vector functions. So this first section is quite a bit of background. We're going to talk about what is a vector function, how do you graph a vector function, and then we're going to end looking at some limits and continuity. So before we jump, though, into what is a vector function, we need to review parametric curves. And so we see that we can represent some curve in 3 space with a function for x, a function for y, and a function for z. And generally, our functions are in terms of some independent variable t, which often represents time. So this is a parametric curve in 3 space. If we wanted it to be in 2 space, then it would just be x and y, and we wouldn't have that z. So that set of parametric curves represents a path in space that is traced in a specific direction as t increases. And if you remember from when you first learned about parametric curves, that's called the orientation. The domain of t is generally all real numbers unless specified otherwise. And so parametric curves give us ways to show orientation, show movement, and often graph things that are much more difficult to represent in 2 space with just a normal Cartesian equation. So that is going to lead us to what is a vector valued function. So our vector valued function, we're going to denote as a vector r, or sometimes it's written as r of t, just meaning that t is our independent variable. And it looks very similar to what you have above. You have a function for x, a function for y, and a function for z, but it gives us a vector. So here's what's important in terms of understanding what this representation actually means. At any given value of t, r is a vector whose initial point is at the origin and whose terminal point goes to that point. Okay, so the domain, all real numbers, range is going to be a set of vectors. So we're going to look at an example, draw it on in this next spot to understand exactly what I'm talking about. So let's say that we have just some vector valued function, and it's defined by f of t, g of t, and h of t. So then r of 0, let's say, is going to give us some vector f of 0, g of 0, h of 0. So if we go to start by graphing that, okay, so what that represents is some vector that starts at the origin and ends at whatever that point is. So let's say that this point is f naught, g naught, not really, f of 0, g of 0, and h of 0. So generally we would call this vector r of 0. Okay, but really what we care about is this end point. And then maybe we have another vector when we plug in 1 that ends up here. And so this vector would be r of 1, let's say. And so on and so forth, plugging in any real values of t. And then maybe when we do r of 2, it comes down here. So this is our vector r2. Okay, so then the actual graph of r then does not contain all of these vectors, but it's when we connect the tips of these vectors. So starting here and going around, and then it would keep going. So this then would be our vector r. So that's what this point says. The graphs of these vector valued functions really just contain the curve that's traced by connecting the tips of the vectors. So we don't care about the individual vectors themselves, we care about where do they end. Okay, and we can graph these in 2 and 3 space. We're gonna look at some examples of both. So let's take a look at this example number 1. Graph r of t, which is 2 cosine of ti, subtract 3 sine of tj, and t is between 0 and 2 pi. Okay, so another way to represent this, just so you know before we jump into the graphing, is we can write it parametrically. So we can write x is equal to 2 cosine of t, and y is equal to negative 3 sine of t. So that is the parametric representation. And that might be helpful to you. My suggestion for you would be to make a table. You're going to plug in some values of t and find out what points does it give you. This should actually be 0 to 2 pi. Sorry, 0 to 2 pi. It might be a good idea to just start with 0, pi over 2, pi, 3 pi over 2, and 2 pi. That's what I would start with, see what points it gives me, and see if I can figure out what the shape looks like. So if we plug in 0, we're going to get 2 for x and 0 for y. If we plug in pi over 2, we get 0 for x, and then we get -3 for y, and so on and so forth. Here's the rest of the table. Okay, so then graphing this. The biggest y I ever need to get to is 3. And for x, I only need to get to 2. And at this point, you might see what's happening. Okay, so I'm going to start by drawing these as the vectors. So our first vector is 2, 0. So it's the vector that ends in that point. And then we go 0, -3. So that's the vector starting at the origin that ends at 0, -3. Then we have -2, 0. And then we have 0, 3. And then we're back to 2, 0. Okay, so hopefully what we can see is that as we go around, what we end up doing is forming an ellipse with clockwise orientation. And if we were to plug in other values, like we were to plug in pi over 4, 7 pi over 6, things like that, we're going to get vectors that keep bringing us out to this ellipse. In this case with the orientation, it's helpful to show where we're starting because it's not clear where we're starting. So we start at that point, 2, 0. So that is the first graphing example. We're also going to take a look at another graphing example that is in 3 space. So that's this one at the top, 4 cosine of t, 4 sine of t, and t. So I would start out exactly the same way with a table. So we have our values of t, which gives x, y, and z. We're not told the bounds on t, but because we have sine and cosine, we know hopefully that we're going to be resetting every 2 pi rather. So I would start with the same values, 0, pi over 2, pi, 3 pi over 2, and 2 pi, just to see what's happening. So if I plug in 0 to the above equation, I'm going to get 4, 0, 0. Pi over 2 will give me 0, 4, pi over 2. Pi is going to give me -4, 0, pi. And then we get 0, -4, 3 pi over 2. And then 4, 0, and 2 pi. Okay, so this is a little interesting. What we see is between x and y, it looks similar to what we had before with the previous example. We have a circle. But then what this z value is doing is it's a circle almost moving up. So you all know from some of my previous videos that my drawing is not amazing, so stick with me. Hopefully I can manage to draw this one okay. We are going to have some negatives, so I would dot in those negative axes. Okay, for simplicity's sake, to not cloud up this graph too much, what I'm going to do is I'm not going to draw in the individual vectors. I'm only going to draw in the point. So for this point 4, 0, 0, I'm not going to draw the vector that gets us there, but I'm just going to put the point. So we know, though, that there's a vector that ends at that point. Okay, so then we have 0, 4, and pi over 2. So that's about here. And then we have -4, 0, and pi. Which is about there. And then we have 0, -4, comma 3 pi over 2. 3 pi over 2 is about 4.71. So that's about here. Okay. So I'm going to just start with this part of the graph right now. So we're starting at this point here, and then I'm going to trace. My graph goes, ooh, that was not great. My graph goes up, keeps going around, and then eventually it's going to come back down and keep going. So here's our orientation. It's a little difficult to picture what this actually looks like, and so a lot of times what people will do, even though my graph is not great, what is happening is they'll draw in a cylinder just to show a little bit of perspective. So this is not part of the graph, but it should show the perspective of what's happening. So what that blue is doing is it's circling around this cylinder of radius 2 going up. So it's circling or tracing around this cylinder of radius 2, moving upwards. And of course, it's going to keep going as t gets bigger. So that is the graphing part of vector functions. What we're going to do right now is move on to writing line segments. So in example 3, we are going to find vector and parametric equations for the line segment that joins A and B. This is something that we've done before. So A, we're going to consider our initial point, and B is going to be our ending point. I'm going to use vector R to represent the direction of AB, so the vector that goes from A and heads towards B. So I'm going to do -5 subtract 1. So I start with B and then A. So -5 subtract 1, 1 subtract -3, and then 7 subtract 4. And this gives me -6, 4, 3. So my vector representation then, if I use this vector of direction and my starting point, is going to be 1 subtract 6t, -3 add 4t, and then 4 add 3t. So that is my vector representation. Now, that's the entire line, though. We just want the segment, so we're going to restrict t from 0 to 1. And if you try that, if you plug in 0 and then you substitute in 1, you're going to start at A and end at B. So that's our vector representation. If we want parametric representation, x is 1 subtract 6t, y is -3 add 4t, and then z is 4 add 3t, again with t from 0 to 1. Okay, next thing we're going to talk about is example 4. Find a vector function that represents the curve of intersection of x squared plus y squared equals 1 and y plus z equals 2. Okay, so first thing, let's talk about what do these look like. X squared plus y squared equals 1 is a cylinder. So it's a circle of radius 1 that moves along the z-axis. And then y plus z equals 2 is a plane. Okay, so there's a few different ways that we can go about this. One item that you could do is you could, in the second equation, solve for y and substitute in the first, and then you're going to end up squaring it. Or what we can do is we can find some parametric representations. So if we start with this cylinder, you've seen from some of those graphing examples that we can represent this cylinder parametrically, where x is cosine of t and y is sine of t. In one of the previous examples, in example 2, our x was 4 cosine of t and our y was 4 sine of t, which gave us a circle of radius 4. In this case, our radius is 1, so we get 1 cosine of t and 1 sine of t. And then we know that t is between 0 and 2 pi. Okay, so that takes care of the cylinder. If we look at the plane then, all we need now is a representation for z. Well, if we solve for z, we're going to get 2 subtract y. And based on the y above, that means that z is 2 subtract sine of t. Again, with t being from 0 to 2 pi. So if we want a vector function then, r of t in this case is going to be cosine of t I, add sine of t j, add 2 subtract sine of t k. Or you could also write that in bracket notation. And then, of course, t is from 0 to 2 pi. Okay, we got a few last things to talk about. On the next page, we're going to talk about domain, and then we're also going to get into limits and continuity. Okay, so domain. This first example, find the domain of that vector valued function. And in the box, it tells us the domain is all values of t for which our vector valued function is defined. Okay, so this probably is going to be fairly intuitive, but you're going to have to find the domain of each individual component. So our x is natural log of t subtract 1, our y is e to the t, and our z is square root of t. So ignoring the x for a minute because I don't really want to think about natural log just yet, for y, our domain is all real numbers. So t can be any real number. Probably a better way to write this is t is an element of all real numbers. For z, t is going to have to be greater than or equal to 0 because we're not going to take the square root of negative numbers. Okay, so then for the natural log, we know the argument of any log has to be greater than 0. So if we think of a number line, the left side of this inequality is going to be 0 when our t value is 1. Above that works, below that works. So our domain for x is negative infinity to 1, union 1 to infinity. So our overall domain then for r is going to be where all of these are true. So our domain then is going to be 0 to 1, and then 1 to infinity. Okay, last thing to talk about, like I said, is limits and continuity. So starting with limits, if we have some vector valued function, then the limit as t approaches a of that vector valued function just means you're taking the limit of all three component functions, assuming all three of those limits exist. So let's look at example number 6. We have a vector valued function in 3 space, and we are finding the limit as t approaches 0. So limit as t approaches 0 of r of t is going to be the limit as t approaches 0 of t squared, and then that'll be my I component. And then the limit as t approaches 0 of e to the t, and that'll be my j component. And then the limit as t approaches 0 of negative 2 cosine of pi t, and that'll be my k component. Okay, so this limit right here is 0. That should be it. This little limit here is 1, and this limit is negative 2. So what that tells us then is that the limit as t approaches 0 of r of t is 0i, add 1j, subtract 2k. Now, of course, you don't need to write that 0i, but I'm just going to write it just to be safe. Okay, so let's take a look at example 7. So we're finding the limit again as t approaches 0. So I'm not going to write that limit 3 times for each function. I'm just going to find that limit. So if we substitute in 0 to this first function, we're going to get 0 plus 5 over 3 plus 1. Nope, 0 plus 1, which just gives us 5. If I substitute 0 into the second one, I get 0 over 0. And then the third one, I'm going to get 0 over 0 again. Okay, so this is a throwback to Calculus 2 or Calculus BC. Anytime you get 0 over 0, if you remember, you're going to use L'Hopital's rule. Remember, you can also use L'Hopital's rule if you get infinity over infinity. L'Hopital's rule just says take the derivative of that function. Okay, so what I'm going to do then is I'm going to take the limit as t approaches 0 of r of t. And that first function stays the same. The second one, because it's 0 over 0, I'm going to take the derivative. So I get sine of t over 1. And then the third function, again, I got 0 over 0, so I'm going to take the derivative. Now if I take the limit of each individually, we already knew we got a 5. Now if I substitute in 0 here, I'm going to get 0. And if I substitute 0 in here, I'm going to get 1. Okay, last very quick topic is continuity, and this should be familiar off of the continuity that you've done previously. A vector function is continuous at a specific value of a if the limit as t approaches a is equal to the value of that function at a. So real quick, is the vector in number 6 continuous at t equals 0? Yes, it is. All we did was plug in t equals 0 to each of the 3 functions. And in number 7, definitely not. And that's because y and z were not defined at 0. Okay, that was your intro to vector-valued functions. Hopefully that makes sense. When we move on to the next section, we're going to be looking at derivatives and integrals. Thanks for sticking with me.